PhD at Harvard. David Nelson, is that correct? And then it was a postdoc at Chicago with Pasha Wigman. And now he is a professor at the University of Colorado Boulder. Thank you for coming to our workshop.
No, it's a great pleasure to be here, and I thank the organizer for putting this nice workshop together, inviting me to speak here and to visit this beautiful city. It's my first time in Sweden. It's really wonderful. People are really friendly, and it's really a pleasure. So it's also, the workshop's been very stimulating. So I want to tell you about some work that is somewhat dated at this point. Goes back to a semester that I spent in Berkeley in collaboration with Ashwin Vishwanath. We talked and based at least in part on this work that we did with Ashwin in 2008. But it's rooted more in a bigger program of trying to understand some aspects of cold fermionic atoms that interact with Feshbach resonant interactions and are imbalanced. We've heard already a little bit about imbalanced systems last week, so there'll be a little bit more of that today. That's sort of the physical setting, but there'll be a lot more. Well, there'll be some new things that take place in that setting, and that's what I want to tell you about. So it's based on the short paper that was appeared in 2009, and then there's a detailed preprint that I'm finishing up that will sort of support much of the things that I'll talk about. It has a lot more information. There's a parallel work, two works by Achterberg and also Kibelson Fradkin's group that appeared about the same time that explores quite a bit of, that has quite a bit of overlap with what I'm going to talk about, but in slightly different systems. Well, this work focuses on high DC superconductors and looking at stripes and continuing the program that Kibelson and Fradkin have been carrying out for quite some time now. Achterberg is also interested in Larkinov-Chenikov-like states that I'm going to talk about. But the big distinction of both of these works, as you will see, and some of the richness that things that I'm doing will come out, has to do with the fact that they are looking inside a crystalline, they're looking at these states inside a crystalline environment. And much of what I'm going to talk about very much depends on, or at least much of the richness depends on being an isotropic environment that is offered to you by cold atoms. So cold atoms are intractable. You don't have the additional ingredient of a crystalline potential, and that's going to be really important. Okay, so let's see. So let me start out. So the outline will be, I'll give you some introduction, background on the imbalanced Fermi gases and the resonant interactions. Then I'll spend a little bit of time motivating why we might be interested in these Larkinov-Chenikov states. Describe a little bit of microscopics of what is the BCS-like theory of these resonant crossover theories, resonant Fermi gas crossover theories have to say about the possibility of realizing such a state. And then, for the most part, this is really the most interesting part that we'll focus on, really not the question of whether the state exists, but whether, if it exists, what are its properties. And just to kind of jump ahead a little bit, it's pretty amazing. The subject is roughly 45 years old, goes back to Larkinov-Chenikov affair. And as far as I know, as far as I can tell, that 45 years has been spent almost exclusively been focused on microscopics and understanding of whether this state can be energetically favorable. Okay, the states that I'm going to talk about. And there's virtually nothing that's been written about or discussed about the properties of the phase. So meaning, you go beyond mean field theory, assume the state is stable, and ask about what are its properties beyond sort of a mean field BCS-like description. And that's sort of what I decided to try to study 2 years ago. Namely, assume the state is stable, leave aside this complicated question and somewhat model-dependent question, system-dependent question of whether microscopically that the system wants to have a state like this at an energetic level. Assume that it's there, and then ask, what are the fluctuations like of the state? It's way, way beyond mean field theory. But, okay, and so then so this part is the kind of the meat of what I'm going to describe. So it sort of asking what is the Goldstone theory of a system like this? How is it different from a conventional superconductor? What are the fluctuations like, and how stable is it? Even if it's energetically stable, it doesn't mean it's stable to fluctuations, once you include thermal and quantum fluctuations. And then there's all kinds of interesting things that appear, and there's really a soup of phases that appears. And so the message will be that you shouldn't really be thinking about Larkin-Ovchinnikov state as at a midfield level, we think of it as a single state. In fact, these two states are usually lumped together. But really, the message will be, you really should think of it as a class of states, and they're distinguished by what symmetries they break. And this class of states actually has many descendants that are disordered, partially disordered version of these Larkin-Ovchinnikov states. And they naturally appear. So let me go way back and start out reviewing first Feshbach resonances in these Fermi gases, and then talk about imbalance. So one of the most important and most fruitful knobs in this business of cold atomic gases that's been introduced in 2003, I think, is this Feshbach resonance. And basically, in addition to the scattering continuum between two atoms, there's Feshbach resonance occur when there's a nearby bound state in some other channel of scattering between these two atoms. And so the wonderful thing is that this bound state, or quasi-bound state in this additional channel, can be tuned relative to this scattering continuum, so-called open channel. And so and you can tune it with a magnetic field by virtue of the fact that these two different internal states of the two-atom system have a different magnetic moment, and so then they shift differently, respond differently to external magnetic field. And so as a result, and they're coupled together by hyperfine interaction, so as a result, you can strongly affect the scattering between atoms that live in your trap are very strongly affected by this nearby two-particle resonance. And so the particles are scattered resonantly in sort of a cartoon-like fashion. You can think of it as when they come together, rather than having a point-like interaction, you have a very strongly energy and momentum-dependent interaction between these atoms. That's because they go into, through this hybridization, given to you by hyperfine interaction, they go into this molecular state, they bounce around in it for a while, and then decay back out. If this detuning, omega, is positive, if it's negative, then you have a true bound state, and you can fall into it and make true two-body bound state, so-called molecules. And so as a result, when this detuning is, so you focus on when this detuning is small, and then as this detuning goes to zero, your scattering length diverges as a function of the magnetic field. So, consequently, you can tune interactions very strongly, resonantly through this application of the magnetic field. And it's been a very fruitful knob to explore all kinds of physics. You can now take these atoms and put them in the optical lattices. You can do imbalance. You can look at resonances. This is the S-wave resonance. You can look at P-wave resonances. And all kinds of richness that comes out. But this is sort of the background for much of that physics. And so some of the things that this knob has so fruitfully provided for us is, so one of the most striking ones is the realization of S-wave superfluidity, paired superfluidity in these fermionic cold atomic systems, and it allowed us to really explore this BC-SBC crossover that probably most of you know very well and work on. But it's also gave us a possibility of realizing P-wave superfluidity, where the story is not as successful there, but it's definitely, there's been some progress. So for example, they've been able to make P-wave molecules using this P-wave analog of this Feshbach resonance. Unfortunately, these molecules are not stable enough to allow condensation of these molecules. And at the moment, it's not clear whether this is a fundamental problem or not. If it's not a fundamental problem, and maybe going to a different atom, different system, this problem can be solved. But maybe looking at it in the lattice systems, then it would be a nice route, cold atom route to a P-wave superfluidity, and therefore, allow you to realize all the beautiful things that P-wave superfluids provide for you. For example, Majorana zero modes and all kinds of non-Euclidean statistics and other interesting things. So the other axis in this general class of systems, and that's the one I'm going to focus on for this talk, is polarized superfluidity, where so-called polarized superfluidity, or equally, sometimes people refer to the imbalanced superfluidity, where you consider what happens in the system, this S-wave Feshbach resonance system, when you have you frustrate the superconductivity or pairing by making the number of species that pair imbalanced. So you don't have a matched number of red and green or up and down atoms. Did you have a question?
So about the P wave, can you tune across the BEC in principle? I mean, if there's no fundamental issues, can you tune across the BEC BCS transition?
Yeah, you can in the same
Exactly
the same mechanism. You can do it through the resonance, exactly the same way in the field. And in fact, it's no longer one of the things that came out of our work on this subject with Victor is that, and that's one of the reasons we looked at it, is that it's really much richer. Now your order parameter is now a three-component complex order parameter, and so even at a classical level, there's all kinds of phases and phase transitions that you can do. So it's no longer just a simple crossover, simple boring crossover that's been so focused for so many years, like in the S-wave case. But there are these, but there's actual phase transitions. But in addition to those, when you tune through BC crossover, there's actually a topological transition when your chemical potential changes sign, where you go from weakly paired P wave to a strongly paired P wave.
Right.
So yeah.
And that is a nodal to nodeless transition as well.
In 3 dimensions, for example. In 2D, it's the kind that Reed and Green discussed.
Yes.
So this is a very interesting subject. Unfortunately, it's been sort of stalled somewhat, despite our efforts to kind of convince experiments to work on this. It's been stalled by this lack of stability of molecules that are P-wave molecules.
Next question.
Yeah.
So if you want to utilize Feshbach resonance, then the channel by magnetic sublevel will be confined. It will have to be specified. In contrast to the spinor case. So I'm wondering whether this P-wave superfluidity can have a richer structure than the superfluidity systems, where magnetic sublevels is not confined to a specific one.
What do you mean by?
So in a superfluid helium-3,
Right.
For example, in the A phase,
You mean the orbital states? Or?
orbital space is available, but in this case, the orbital space is replaced by a spin projection space. But in order to use Feshbach resonance, we have to specify a particular magnetic sublevel. So that's in this sense, I think the P wave is turned out to be a P wave scale.
No, so there's a spin part and there's an orbital part. So the spin part, you use the same hyperfine state. So you use the same species, single species.
Yes,
so that's like fully polarized analog of in the helium. It's like fully polarized strong magnetic field. So there's only single species. But there's still orbital degrees of freedom. And in principle, you could have phase transitions, as we've shown. There are phase transitions between, let's say, a state that has zero projection of the orbital angular momentum to a state that has P plus IP-like state. So that's, but let me not focus, let me move on, because this is not really the subject of my talk. This is just sort of to put it into a broader perspective. And what I would say here is that much of this we understand actually quite well, despite of a lot of activity that's still going on. It's a question of, what do you mean by understanding? So, but let me say, even in the S-wave case, which is in some sense most challenging because there's no transition, so there's no point to perturb around, there's a very a description that I'm really fond of in terms of this two-channel model, where there's really a small parameter, and that's parameter is basically the width of this resonance, or how we. The strength of this coupling. So, and so if the coupling is very weak, which in realistic systems is actually not, it's strong, but if it's very weak compared to the Fermi energy, then you can have you can carry out complete and quantitatively accurate description all the way across the BCS-BC crossover. So there's all the problems that you face with when you have a broad resonance are not there. You really have a small parameter, it's completely quantitatively controlled. So you can think of this as a physical parameter. You can also think of it as a mathematical parameter, much like we expand in field theories when we have introduced additional, maybe less than physical parameters like log n or epsilon expansion. So I'm quite fond of this, and this is something we emphasized early on with Victor when we studied when we were doing the S-wave case. For the broad resonance case, at least for the system at hand, there's not there's a good qualitative description, but there's no quantitative description across the transition, except if you introduce. You can make it quantitatively accurate if you do 1 over n or large n or epsilon expansion. And so even in the broad resonance case, there is really a qualitative and quantitative, in a sense, understanding, like a solution all the way across Feshbach resonance. And so this is somehow not sufficiently well appreciated, at least in the cold atom sort of general AMO community, that this S-wave case is also, both of these cases really understand quite well. Okay, so but now what I want to do is I want to focus on this imbalanced axis. And so what I want to ask is, and this is motivated by a variety of realizations. So, for example, superconductivity in presence of a magnetic field or quark-gluon plasma, etc. You could have also not Zeeman field, but simply two fermions that would like to pair, but that have different masses or different dispersions more genetically. And so what we try to argue quite some time ago, that cold atoms are really a very natural realization of the system, simply because unlike, let's say, superconductors in magnetic field that were originally motivated Folder-Ferrier, Larkin, and Chinnikov to look at these systems, or even before them, here the analog magnetic field is just a Zeeman field part. So in a sense, the physical magnetic field, of course, comes with two parts. It has the orbital part and the Zeeman part. And the orbital part, usually under standard conditions, 3 dimensions, dominates over the Zeeman part, and so it's very hard to access the physics I'm going to describe. But here in cold atoms, it really is in fact, you control the difference between the imbalance between the two species of atoms that are pairing. And so in a sense, this is a very natural setting in which to explore this frustration of superconductivity to imbalance. And so really what we want to do is, and that's what I'll describe, is understand what happens to the BCS-BC crossover when you put on this additional axis, namely the imbalance. And so this was, we studied this with Dan Sheehy. The general subject is, of course, very old in the context, in these other contexts that I mentioned, in nuclear physics and condensed matter physics, superconductors in the presence of the magnetic field. But our contribution to the subject that came in 2005 was to try to extend that understanding that existed deep in the BCS limit all the way across the BCS-BC crossover. So really asking what happens to the BCS-BC crossover in S-wave Feshbach resonance systems when you turn on this additional axis. So our contribution is to add this part of the phase diagram away from this deep BCS limit. And the story is somewhat boring. It turned out to be quite boring. Basically, almost over a large portion of this phase diagram, this is where the BCS-BC crossover takes place. This is your either molecular superfluid or atomic superfluid. Sorry, either molecular superfluid or BCS superfluid. So this is the so-called BEC limit, BCS limit. Basically, as soon as you put any imbalance, this is this fractional imbalance of polarization, the system phase separates into a normal, roughly speaking, separates into a normal state and paired superfluid state. The slight richness of it, or slight inaccuracy of that statement, is that there is a phase here that's quite, at least at mean field level, it looks quite boring and quite obvious. It's a state in which, if you have an imbalance, this is so-called magnetized superfluid, if you have an imbalance and you're deep in the BC limit, where you have a two-body bound state, basically all the atoms that can pair up into tightly bound molecules that are bosons, those bosons both condense, and they coexist homogeneously without phase separating with a fully polarized Fermi sea of the remaining axis atoms. So it's a fairly simple state, sometimes incorrectly from my point of view referred to as a Sarma state, but the idea is that the state, important observation, the state only is realized on the BEC side of this diagram. There's no such state, at least within the mean field theory, that happens when you have a Fermi surface. Okay. So the other interesting state that occurs is the extension to the phase diagram of the well-known Folder-Ferrier Larkin of Chinnikov physics. That's the focus of this talk. So this phase diagram was very nicely extended. So we proposed it in 2005 at zero temperature. We didn't explore the thermal effect at all. There was a very nice work by Parrish et al. That extended the phase diagram to finite temperature. And really, there's additional richness that takes place when you look at finite temperature.
Just want to make sure I understand. You have phase separation between a balanced superfluid and a magnetically ordered normal state, or so when you have
Well,
a
it depends where
imbalanced
you're
spin,
looking. So where
in that upper right-hand corner.
So here,
Yeah.
strictly speaking, it's a phase separation between singlet, fully gapped BCS and a Folder-Ferro state. And then the Folder-Ferro state undergoes a continuous transition. So you can think of it as a first-order transition from a BCS state to the Folder-Ferro state, and then Folder-Ferro state across, exists across this very narrow sliver of parameter space, and then gives up continuously into the normal state, which is polarized. So but it's not fully polarized. So this is the full polarization, and then delta n over n equals 1. So here you have basically two Fermi surface normal state.
What's underneath Folder-Ferro, the gray area underneath?
This is if you do it in this ensemble, which is relevant to experiments, where you're fixing the total number of particles and fixing polarization. This is coexisting state between Folder-Ferro and BCS state. So it's an inhomogeneous state where the system phase separates into Folder-Ferro and the BCS state.
But if you move to the last side,
Okay, so there are these so-called tie lines, which I actually didn't indicate here, but they are in our paper, which tell you what is coexisting. So there's a tie line that goes in like this. So to the right of it, what's coexisting is this BCS state and Folder-Ferro state. If you move past that, then what will coexist is this magnetic superfluid in the normal state. So it's a question of where you are. Which minimas, there are multiple minimas in the system, and it's a question of which minimas are becoming degenerate and coexisting. So that's somewhat complicated. It's a complicated energy landscape.
could you give some details about the controllability of this description? Because you were mentioning about controlled description.
Sure.
Gamma is small, so I guess.
Sure.
it's
So
under the
we first worked this out, motivated by what we did with Victor and this message we were trying to send, even in a balance case, that really the only way you can control your calculations is in this two-channel model where there's actually a boson, real boson in the system, and pairs of fermions, and they're coupled together through a Feshbach-Boson coupling. So in that limit, when that coupling is weak, it extends to this. So this is at zero temperature. This is completely controlled, and you can completely calculate everything. When width of the resonance over the Fermi energy is small enough.
Then you get this phase diagram.
Well, the phase diagram. This is now okay. So this
In
particular
proper,
phase.
in terms of, I understand.
No. So you get this kind of phase diagram qualitatively.
Yes.
In that model, it's slightly different shape, but qualitatively
Right.
it's exactly the same
Qualitative.
thing. Yeah. Absolutely.
And
Now,
then
if you
just-
do now instead, I mean, this particular phase diagram was worked out for a single-channel model where it's no better or worse controlled than BCS-BC crossover, which gets the general features right, but I don't trust it quantitatively.
But you have a Monte Carlo calculation of this phase diagram,
Sure.
which is
Okay, so that has its own issues, but.
But it looks like this
The
is
Monte
just
Carlo
divided
isn't
a
here.
little bit.
No, absolutely. So I think there's now a consensus on this phase diagram, certainly qualitatively. Now, quantitatively, okay, so there's, I think, pretty good agreement as well. The question is agreement with what? If you do, there's no quantitative analytical calculations that you can trust here. So, you really have to defer to experiments in Monte Carlo. If you want to understand the phase diagram, just even the balance case for the wide resonance, which is of interest to experiment.
Even numerically, there is a hope that, say, fixed node Monte Carlo gives an accurate result, but it's a hope.
Yeah. But it looks like this, it's just the lines are moved a little bit.
Absolutely, absolutely. I mean, there was a lot of, when we were doing this work, following our work, there was a lot of papers that tried to construct this kind of phase diagram. There was a lot of controversy. There were many versions that followed that did not agree with this. Okay, and part of the reason is because what people tend to do, and sort of a message I've been trying to, well, we've written on the subject. I mean, so what people try to do, it's so used to doing in the balance cases, they solve gap equations. Okay, so you got some numerical solution, and you don't really worry about the energy landscape. You go and you solve the gap equation. So when you solve gap equation, if there's a single minimum, if there's a continuous transition, that's not a problem. That's really just the same thing as looking at the energy, and really you don't have to look at the energy because there's only single minimum at any one time. When you're looking at this imbalance case, the landscape has many more extrema in the energy. And so what people were doing for a while is they would solve gaps equations for this imbalanced case, and they would find solutions, and they would identify those solutions with phases, and they would put them on the phase diagram. Okay? But those phases are really just extrema. They're not really the minimums, and it's much more subtle to really explore what the energy is doing, especially when you have these first order, phase separations and other phenomena. Yeah.
So is this epiphenomenal stability region consistent with Monte Carlo results?
I don't know. I don't know if somebody's up on what is the situation with Monte Carlo as far as the FFLO goes.
Oh, it's not done yet.
It's not
I
done.
think FIXNO didn't do FFLO yet.
So they
ignored FFLO.
They just ignored it.
Yeah.
Okay. I'm not sufficiently up on this. So one of the messages that came out here that's often cited from our work is that just like the earlier calculations deep in the BCS limit, is that this state is very fragile and it's only exists over this narrow sliver. Our contribution was to show how the sliver closes as you go to stronger coupling, okay, and where it closes. Now, part of my message will be that I actually, in the motivation for studying the state, is I no longer believe that conclusions we made based on our calculation of this phase diagram is no longer warrants this interpretation. I mean, it could be this way, but we don't have, conclusions that we drew from it that. In other words, we understand the upper boundary very well. The lower boundary, I would say, is not, the conclusion we made about the location of the lower boundary is no longer warranted. That's my opinion, and I will try to back it up for you. And so I think it's still an open question in my mind where this lower boundary is.
Excuse me.
And so it could be much more stable than this R mean field analysis suggests. Yep.
I'm just wondering, in the deep BCS limit, isn't it possible to do reliable calculations
Sure.
using the small parameter?
Sure.
So, therefore, I believe that calculations at the deep BCS limit should be reliable. Is that right, what I'm saying? In principle.
No, even there it's not real. Well, let me think. Depends how you do this calculation. There's sort of two approaches to understanding, to trying to describe this. One is using Ginzburg-Landau theory, okay, where you actually expand on the order parameter, which is justified around this point, okay, because the order parameter, at least self-consistently, if you assume it's small, then you can expand it and see if the transition is continuous. The other way is doing BDG solutions, which is the way Folder-Ferrer did it, and many works afterwards, and that's the way we did it as well. The problem with that is, so that allows you to get away from the, seemingly allows you to get away from the region where the order parameter is small, and really treat the energy non-linearly in the order parameter. So it allows you to seemingly extend away. The problem there is you have to make a choice of what the shape of your order parameter is, how many harmonics you're going to keep. And so that choice is very limited, and analytically people have not been able to handle, we certainly weren't able to handle anything beyond a single harmonic. And a single harmonic, I'm going to try to argue, is qualitatively different than two harmonics, Q and minus Q.
Just to comment further, in principle, calculation is controlled in the BCS limit. But because the ground state is non-uniform, it is actually very difficult to compute energy differences. It's a little bit like looking at the ground state of a vortex lattice.
Exactly.
In the BCS limit, in principle.
Yes, this I understand.
Yes.
Of course.
So
I only said that if you have a small parameter in this theory, then you have a way to do things.
But even,
So the answer to your question is you are correct, but in a trivial way. That's what I'm saying.
I would like to say that I am correct in a non-trivial.
okay. No, so we're in agreement. We're in complete agreement. But in practice, we're about this point.
May I ask you a question? So FFLO continues all the way to minus infinity?
Supposed to be correct, and that's not, that's old work of, Larkin and Chinkerfold.
I guess the bottom line with the controllability which Jor was mentioning is that you never know whether you found the true ground state or
Yeah,
you can
it's
find something better.
In
right?
principle, if you could solve non-linear, non-uniform,
Right,
partial
yes.
differential
You found
equations.
something, but the real problem is to prove that it's the best.
Exactly.
No, sorry. So it's a little better than that, actually. So when you expand around this line, the upper critical field, it's very much like HC1, HC2.
That you
orbital
can
and
solve.
You can solve because there, the order parameter, you assume is small, and then you can do a Ginzburg-Landau expansion, just like Larkin-Ovchikov did. And so it's self-consistent. What you're seeing is there's infinite number of harmonics are going negative, are unstable. So the question is, so any harmonic with a particular magnitude of a wave vector, but arbitrary direction, is going unstable. So that's why the location of this boundary is undeniable. Now,
But that's assuming it's second order, right?
it's assuming second order, but at least it's self-consistent.
Right,
You say
sure.
it's small, assume it's second order, expand. Maybe at some shorter, much longer scales it jumps, but it jumps by a small amount. You assume the order parameter is small, so you can expand. You trust it. The problem is what happens when you go deeper in. Once you go deeper in, it's going to be nonlinearities, as Latko pointing out, very much like in a vortex lattice, that are going to decide which precise combination of these Fourier coefficients of the order parameter they're actually ordering. And so if you make a wrong choice, well, first of all, in that expansion, you cannot trust that expansion down because now delta is large. So that's first observation. Now, if you do it with BDGs, you can trust the calculation of the energy of the ground state energy for arbitrary large delta. However, then you have to have a good choice for the shape of your delta, for your choice of your Fourier coefficient. If you make the wrong choices, I will try to argue we made and everybody else makes. Namely, you take a single harmonic. That is a very unfavorable. It may be as favorable near HC2, but it's quite unfavorable deep away from HC2. And so, therefore, I don't think there's a reliable calculation right now to tell us how extensive this region is. And so, my hope is that it's quite a bit more extensive than our calculation suggested. So, okay, so there are a lot of experiments. Many of you have already seen this from last week. That there are primarily two groups that have studied this and have seen the phase separation. They look in the trap, and the primary feature that they see, this is Ketterle's group and Hewlett's group, the primary feature they see is that in the center of the trap, you have a fully paired core where the two species, the red and the black, that are pairing are matched in their densities. So that's a signature of singlet BCS state between these two. And all of the imbalance, the extra particles, are pushed out to the side. So the magnetization, if you wish, or the polarization is pushed out to the side. And so this is a common feature that's seen. These experiments are in a pretty good agreement, but there's some discrepancies that are, okay, so there's still open questions of how to resolve these discrepancies, although some people have an opinion now of of how to resolve them. Hewlett argues that LDA is not appropriate and sees the effects of, arguably sees the effects of surface tension across this first order transition, while Ketterle disagrees with that. And so there's a few other features. Of course, these experiments are actually done on drastically different systems with drastically different parameters. So here there's quite a bit more particles. So these are smaller condensates in Hewlett's lab. And also these are, in Ketterle's experiment, the traps are a lot more isotropic. Here the anisotropy in the trap is like 40 to 1.
Leo, is there an end of this story in between Ketterle and Hewlett? Because Christoph Salomon also very elevated geometries and
Exactly. So
recovered the results of Ketterle.
yeah, that's absolutely right. So this is my next slide. So this disagreement, from my point of view, is a somewhat slight disagreement between these two main groups that dominated this field. Experimental groups dominated this field. Was recently checked by these beautiful experiments by Solomon in Solomon's group last year, and they I think purposely studied a system that has number of particles in the anisotropy of the trap that's quite close to the Rice's group. Okay, but the results they obtain are in agreement with MIT group. Okay, and so the implication is that actually there's something actually experimentally wrong with the Rice's experiment, that there's that sort of these guys vote in favor of Kedley's observations.
And
So-
the same number of particles are different.
Quite comparable. You know, it's a pretty small cloud.
Yeah, I mean, so just to comment, I think the well, Randy's converging towards the idea that there's probably some non-equilibrium.
That's right.
Which we
That's
yeah,
right, which you
there we
guys
go.
explored.
Yeah.
Yeah. So that's actually very nice work. So that's what I'm saying. So there's some interpretation of where this comes from, but it's not.
But this point was also checked by Chris Solomon.
This non-equilibrium spin transport.
Well, one concern was that at Rice, the ramp down time after evaporation was pretty quick, and on the order of 700 milliseconds. And on the other hand, MIT ramped down time is much longer. So one concern was that at Rice there was no equilibrium state. So that's why the Chris Solomon changed the ramp down time from very quick to very slow.
Mhm.
See no change.
I see.
So there's still a lot of mystery about this discrepancy.
So with that background, I want to focus on this fold Larkin-Chinikov state. And so before everything I'm going to say after the slide, it doesn't rely again on the stability of the state. Well, it presupposes, it doesn't rely on these arguments, it just assumes if the state is stable, what are its properties. That's what I really want to discuss. But I want to spend one slide telling you why I think, and I've already said some of those things, why I think it's actually, that this is maybe not a good representation. It's an underestimate of the stability of the state. So I want to consider a state in which there's a fair density wave of some Fourier content. And so what are the motivations for studying something like this? Well, it's stabilized in lower dimensions. So clearly, in 1D, we expect the state to exist. There's some really nice work going back to Matsuo, but more recently was re-examined in context of these resonance systems by Yoshida and Yip, that shows that if you make a domain in the BCS superconductor, delta minus delta domain in an imbalanced superconductor, it actually has a negative surface tension. And so the idea is that this will facilitate creating a state like this, a Larkin-Chinikov-like state. And so my view of this is, and this is kind of a view that's quite colored by what happens in one dimension, is that that you can actually have, you can actually in principle have a continuous transition, in contrast to what it doesn't indicated here, a continuous transition from a homogeneous superfluid that exists at zero imbalance to a Larkin-Chinikov state, and that transition can go along something like the Pokrovsky-Tolopov transition. And this is exactly what happens in one dimension. Basically, as you begin to, as you introduce chemical potential imbalance, for up to some critical, lower critical field, no domain walls enter of this type, okay? But, or of this type. But at some critical value, domain walls enter in a continuous fashion. And what grows is not the strength of the order parameter, what grows is the period, or the wave vector. So at this point, the wave vector, which is the spacing between domain walls, is infinite, but then it's continuously, so here's the representation of the homogeneous state, and then at some point you introduce domain walls that are infinitely far apart, one domain wall, two domain walls, and this density continuously grows. And so this is a continuous way to interpolate between a uniform superfluid state and a superfluid state that has a finite momentum, finite wave vector, finite modulation. And this is quite analogous to what happens in the orbital systems when you have a HC1, HC2 transition. This would be the analog of the Meissner effect. This would be the mixed state, and eventually it saturates. When domain walls begin to overlap, that's what you would call a crossover at the HC2 transition. Okay, so this is what the state would look like. And so the axis, and this is a really beautiful picture, and it's quite accurate. It's not just a cartoon in one dimension, where the axis fermions actually sit on these domain walls. So every time you have a domain wall, you have a mid-gap state. And so then it's, so even though there's some energy cost to make a domain wall, or a little region of normal region, but then you could put a fermion in that. And so this is quite analogous to polyacetylene of Schrieffer, Su, and Heger. And you can also appreciate that this is a microscopic phase separation as opposed to macroscopic phase separation. So qualitatively, it's not, well, it's at least in the same, the system is trying to phase separate. Now it's a question of what these domain walls want to do. Do they want to coagulate into a single region, and then you'll have a macroscopic phase separation. And that would be the analog of type 1 superconductor. Or do they repel, and this calculation has not been done, do they repel, do they want to make a periodic state of these domain walls? And then you would get the Larkin-Ovchinnikov state. But those two states, that's a detailed question, and then very much like in superconductors, orbital superconductors, where you have, there's this distinction between type 1 and type 2, that's a question of a, really a microscopic system and where exactly it falls. So they're not so anyway, it's not such a trouble.
What is the domain walls? I mean, the base of the order parameter changes?
So the order parameter changes for plus to minus, plus to minus.
Can I raise a question about 1D? Actually, frankly, I have a serious problem with 1D because I know that in 1D, actually, fermions are like bosons, or bosons like fermions, whatever.
Yeah, so these distinctions...
And basically, that's what somehow worries me in terms of interpreting this state as a FFLO. Maybe it's just one and the same, but...
It's one and the same. It's no different. It's no different than this state. This state is any... Basically, what I would say is, and this is what I said when you made this comment last week in a different talk, you can think of this state as where there's a spin gap, and the only gapless Lunge liquid is the charge mode.
And this state
and
can
you
be
can call that a
realized
super...
in any dimensions with bosons. In any
Absolutely.
dimensions with bosons.
What changes here is now you close your spin gap, and now there are two superfluids.
I
There are two
drove the
Lunge
system
liquids.
with extra carriers, right? On top of the...
Exactly. So now the extra carriers enter.
Yeah.
It's just a band-filling transition. And that's how Kroski-Talbot, in fact, solved that problem. They solved it by mapping onto fermions when they described the commensurate and commensurate transition, let's say, in classical systems, let's say, of line objects or domain walls. They map it onto a system of fermions and start solving using... And so the point is, the distinction here, there's a single charge Lunge liquid mode here, and here's a charge Lunge liquid mode and a spin Lunge liquid mode. And that's the transition. You shouldn't, in 1D, you shouldn't focus on this periodicity so much. All there is a new wave vector appears for spin, for the extra particles.
Which is the interparticle distance in terms of the particles.
Of the additional ones, exactly.
If I dope with both,
yes,
I see
exactly.
the same.
So the periodicity is
It
not
always
important.
tunes to that wave vector.
Huh?
It tunes to that wave vector
Absolutely.
from
Yeah.
that point on.
But Leo, maybe you can just tell me why people are so much focused on this 1D. In 1D, after Pokrovsky-Tolapov, people have solved the Fermi-Hubbard model exactly with this.
Sure.
It's solved by the Berta-Ansatz.
No, the reason this thinking, well, okay. The reason this picture is so, I like this picture so much is because that exact solutions of 1D Bose-Hubbard model, or Fermi-Hubbard model is, you can't extend that to 2 and 3 dimensions, okay? But understanding it in terms of these qualitative terms allows you to think about that it's not so crazy. It allows me to understand and motivates me, my understanding of how our calculation with Dan Sheehy in 05 can miss all this physics because we're not putting that in. We're assuming a single plane wave. Single plane wave is actually a homogeneous state. So it doesn't have any of this physics. So while it's just as good up here, the upper critical field, it's terrible when you start going in because it doesn't have these nodes in the density. It doesn't have these mid-gap states. As a result, if you assume that state and solve and find the energy, the system gives up much earlier than it would if you actually put in the right ansatz like this. It's just a motivation. Again, what I'm going to talk about is you're going to assume all this. So let me just flash this up.
Maybe for educated people, it's much better not to call it Larkin-Ovchinnikov, but just to call it Latinger liquid, because there is a...
In 1D, of course.
Yes, 1D.
Of course, but I'm not focusing on 1D. So my proposal is, or what I hope is, or what I expect based on this argument, that the picture is actually much more favorable like this. That all the way below this, there's a much larger region of Larkin-Ovchinnikov states. The states that I want to tell you about. I'm quickly running out of time. But
Sorry.
No, it's
so
fine.
You drew the new
we started.
boundary. You drew the new boundary on the basis of this new insight. Is that a...
I don't have a calculation to draw that
So
boundary.
it's an artist drawing.
It's an artist.
So if I asked whether there is a re-entrance, it would be a silly question.
Okay, so it's silly in the sense of I haven't done this calculation, but it's not silly in the sense of the richness that will emerge if I assume these states and then include fluctuations and show you that in fact it's not a single state that lives here. Even if I assume there's a Larkin Chickasaw, there's actually a class of states that lives there. But in fact, my arguments are a little bit better than this. So I'm going to show you. So let me spend one slide on this. So there are these two works. One is done in 1D by Machida and Nakanishi in '84. And so this is their phase diagram for this. And it's precisely this BCS continuously undergoing transition into the so-called Larkin-Ovchinnikov state, one-dimensional Larkin-Ovchinnikov state.
Excuse me, and yet another issue about 1D that we do not have a genuine long-range order in 1D. So basically, LO prime, because...
You can call it anything, it's like sort of saying...
Like Jora said, Larkin-Jora liquid.
You can call it, it's just the semantics.
No,
it doesn't,
because there is no long-range order.
I know, but okay, we've understood. Okay, so we understand and we move on. So, at some point, once and for all, 20 years ago, 50 years ago, whatever, with Kassel-Stauss, we now understand that in 2D, there's this distinct phase, XY phase, that's distinguished, we understand it's probably. So that's, with those caveats, I just don't want to repeat them every time. But as a nickname, I'll call it Larkin liquid. But again, I'm not focusing on 1D. So anyway, the only thing I want to point out here is there was a calculation that was done in '94 by Burkhardt and Reiner that supports this picture. So what they plot is, as a function of Zeeman energy, they plot distance between, or the period of this Larkin-Ovchinnikov state. So this is in 2D. And they put a magnetic field in plane, so there's no orbital effect. And what they find is, in fact, this is the up to 0.65 of Zeeman energy ratio to the BCS gap. You have a gap, fully gapped superfluid, homogeneous superfluid, paired superfluid, and then it undergoes a transition of exactly the kind that I described into this Larkin-Ovchinnikov state, with the period coming down from infinity as the Salton center. And then finally gives up at 0.85. So this is really the only evidence, sort of, non-numerical evidence of this transition. So the fact that outside of one dimension, there's actually the region of Larkin-Ovchinnikov state is much more extended than what we suggested, that some region, very tiny region around here. So it's extended all the way down here. But how is it done? It's done using basically BDG, but then solving them numerically. Self-consistently. So you assume something that I cannot do analytically. You assume there's two harmonics, Q and minus Q, and then actually, you assume a general shape of a real order parameter that is in the class of Larkin-Ovchinnikovs, not necessarily a cosine, and you self-consistently correct that order parameter and solve numerically the equation.
Which equation? Bogoliubov-Lejeune equation?
Well, they
Eilenberger equation.
Huh?
Eilenberger equation.
Eilenberger, yeah. So they solve the analog of BDG equation. I think it's equivalent. It's just they work with Green's function.
No, they are not equivalent.
No. Semi-classical.
Semi-classical
Okay.
version.
Okay. So I'm not familiar with that.
Better than Ginzburg-Landau, but kind of in between Ginzburg-Landau and Bogoliubov.
Because so you integrate over the facet. Okay, fine.
You told us, Leo, that this picture in the lower corner, left
That's
corner,
right.
is in 1D.
That's right.
Why do I have to look at this picture?
Okay, that's why we're not going to look at it. Because I'm going to move on.
I know that going on, which is exact. It's exact Fermi cover.
Fine. So your exact solutions, you can't get everything out of them. Okay?
Oh,
what can
you
you?
got everything, also magnetization and so
That's
on.
fine. That's fine. So anyway, so what I wanted to motivate
These
by this.
people are drawing these pictures. It fits me. Yes,
Okay.
because
Fine.
it's something which is unbelievable.
Okay. So what I want to do now is I want to spend a little time of deriving. Okay. So I want to go to dBCS limit and use the BCS to derive a Ginzburg-Landau theory for the Larkin-Ovchinnikov state. Well, derive the Ginzburg-Landau theory and then ask. So this is, imagine I'm in the normal state, I derive this Ginzburg-Landau theory by integrating out the fermions near HC2, basically following what Larkin-Ovchinnikov did, and then ask what is the instability of this theory when I reduce the imbalance in chemical potential, which is encoded in H. I don't know where it is here. So I reduce H. At some point, the system wants to become a superfluid. And so I want to explore that. And the nicest way to explore it is to integrate our fermions, have an expansion in delta. And so what you find is that, in fact, you get this Ginzburg-Landau expansion with the dispersion, the quadratic dispersion, that has a minimum and a finite momentum. Okay, and this is it. And otherwise, it's very, it's just a plain vanilla Ginzburg-Landau theory, but the minimum occurs at a finite momentum. And so the nice thing is you have a prediction for all the couplings that appear in this theory, which will then tell me a lot about the Larkin-Ovchinnikov state that I go into.
Yeah, just don't worry about the time.
Okay. Well, we started later too. But okay. There's one observation here that will be important. When you have this ordering at a finite momentum, this is something Larkin-Ovchinnikov did not calculate. There's actually, as you will see, as I will show, if you want to get a well-defined theory, you need to go beyond this quartic expansion. You need to actually go to something that's like a current-current coupling. And that's contained in principle in these guys, but you need to extract it. And this is going to be an important ingredient. So just a small caveat. So now that you have the instability of finite wave vector, you can then explore various states. So one of the states, the simplest state, is a single wave vector state that I already mentioned. So this state is quite unfavorable given the arguments that I presented. But it's quite distinct, not surprisingly, from the Larkin-Ovchinnikov state. So sometimes people often carelessly lump this all together, but it's very energetically it's very different, but also from the point of view of symmetry it's very different. Really, it breaks time reversal and it breaks orientational symmetry and has an off-diagonal lineage order. And so really, it's an orientationally ordered superfluid. It's not a crystal of any kind, even though it looks like. So you could think of it as a superfluid with a vector in it, along which there are spontaneous currents. So the state that really I want to focus on, for the reasons that I described in the previous transparency, is the class of states, the Larkin-Ovchinnikov states, that have real order parameter. So it doesn't break time reversal, and so it has orientational and translational order. So it has, you should think of it as a mnemonic Q and minus Q. Okay, so that's a superconducting. So what I'm going to try to argue is that's a superconducting smectic liquid crystal. Okay, and that physics, it's not just a name, will be reflected very much in the behavior or phenomenology of the state. Yes.
But at least you are sure that if you add other harmonics, this will be, at least in some cases, the lowest state.
That's right. So I think this physics here is just a single harmonic. As long as I keep this general structure, I could maybe degenerate the cosine.
No, I'm asking a different question. I'm saying if you add the second harmonic, so actually
so that's
can you prove that this sometimes can be a better state?
That's right.
You can.
You can.
Can I show this?
Yeah.
Yeah. Because it's a very important question.
Oh, you see, you are claiming you are considering this state. Can you ever prove it's a better state?
Well, okay, so Larkin-Ovchinnikov already, is it better than this?
No, I'm
Larkin-Ovchinnikov already.
not asking that. It's definitely better.
Okay, but what's the question?
If I add the second harmonic, can you ever prove that two harmonics are worse than one harmonic?
No, I can't. No, I don't think it's true.
Which means this doesn't exist ever.
This is a cartoon for a class of states that have these symmetries. That's why I want to.
No, I understand, but they never exist in nature.
No,
Okay.
never. You never have a single harmonic.
Okay.
Why would you have a single harmonic? It's a nonlinear.
It's just a question. You just presented, so I just want to
Well,
understand.
it's like describing charge density by a cosine.
Okay.
Or there's never ever
No,
system.
I'm not saying it's single harmonic in a pure harmonic wave. I'm saying there is a second direction, which is not the same.
Oh, a second.
Which
Where's the
makes it a
crystal?
crystal, not
Wait a second. Oh, I'm
orientation.
sorry.
Yeah,
Okay,
why
My
smack
question
now?
was about crystal versus smack.
Absolutely, I don't know that. Okay, I have no, I don't know that. So I'm just focusing. This is the simplest state, and it's extremely rich. Many of the things I'm going to say do not exist in the crystalline states, where you have non-collinear cubes.
Yeah, but I have a very simple question. Can you ever show any model which actually has a symmetric as a better state than a crystal? Or crystal always wins over
I
symmetric?
cannot.
I see.
What do you mean with crystal? Different cues?
No, I'm saying that crystal has
Non-collinear
Q1
cues.
and Q2.
So here there's by this state I actually mean
Q1
any.
and Q2 you have a crystal, and maybe crystals are always better.
Okay, so you want to distinguish between
Absence of
collinear.
translational
So this state only breaks translational symmetry in one direction. So By this, I really mean any combination of collinear Qs or minus Qs.
Yeah,
Okay? Any set of harmonics. He wants to introduce additional Qs that are non-collinear with it, and therefore you'll get a crystal.
Yeah.
I cannot prove this. That's why I said, look, let me assume the state and let me explore its properties. You know, often we explore properties without knowing what model gives the state. We want to understand, understand how various phases behave. In the same way that if you have an ordinary superconductor, you understand that it's described at low energies if it exists by an XY model, then there are various predictions that follow from that.
Then I have a simpler question. Can you show that this state is stable at least locally with respect to small perturbation?
That's the subject of my talk that I'm about to get. Okay. So if the state like this exists, it's actually a very important distinction of this state in cold atoms, unlike crystalline environment, that it's not just a density wave, or pair density wave, it's a symmetric, it's a superfluid symmetric. And so many things follow from it. So let me just show you how this works. This is, from point of view of symmetry, it's very obvious, but somebody had to write this down and work this out. Okay, so the Larkin-Ovchinko order parameter is now a combination of two harmonics, Q and minus Q. And you can generalize this for any collinear, really, deformation of the state. So then there are two coefficients, and those coefficients will complex numbers, Fourier coefficient. They'll have two phases. So immediately you see that there are two Goldstone modes that are going to describe this state. And there's a somewhat more physical way of describing this. If you take a mean of these two thetas, theta plus and theta minus, that's going to be the superconducting phase that sits in front. And then in addition, the difference is the phonon of this density wave. So these are the two physical Goldstone modes of the system. So superfluid phase and superfluid phonon, and a phonon. And so then, if you take that Ginzburg-Landau theory that in the BCS limit I can derive very carefully, because if mean field theory applies, I can, and then take the state, you can derive sort of an XY model Goldstone mode description of these two Goldstone modes. Okay? And so what you get is, there are two Goldstone modes. If you wish theta plus and theta minus, I happen to call them U plus and U minus, which are trivially related by just rescaling. They have, without this gamma, what naively you will get is just this form, which is basically, notice there's an elastic modulus in the z direction, and there's a no elastic modulus for the gradient terms in the perp direction, and there's only the elasticity in the perpendicular direction starts at a quartic order, depending how you count. But it's softer than in the direction. The z direction is the direction of ordering of the Q vector. Okay? So it turns out if you work harder, you actually realize, well, you can look at it from a physical point of view, a symmetry point of view, but also if you work harder on that Ginzburg-Landau theory derivation and you look at high order terms, you realize that this model that you get is not generic. You really actually get something that's distinct. You need something like this, that basically each one of these is a characteristic of a symmetric, and it turns out those symmetrics are actually coupled together. The difference in the two phonons of the two symmetrics are actually, their gradients are tied together. Okay? And there's a physical reason for this is, well, I'll comment on that in a second. So where does this form come from? Well, it comes from rotational invariance of the symmetric. The symmetric, that wave vector could have been chosen in any direction. In contrast to like charge density wave in the crystalline environment, here, this orientation z, well, even though I chose it, it could have been picked in any direction for both of these u plus and u minus. And so as a result, if I take u and rotate it by some angle, this cannot cost any energy. And so therefore, I cannot have terms grad u squared. The coefficient in front of this has to be exactly 0 in the energy. Okay, so this is well known in ordinary liquid crystals. So if you have a symmetric, meaning you went from a state, you didn't just break translational symmetry, you also broke rotational symmetry. This term has to be exactly 0. The word identity that forces it to be 0. And so that's why these terms both come out to be, both for u plus and u minus, you sort of have two symmetrics, the plus symmetric and minus symmetric, that have this dispersion. But of course it turns out that the difference in the phonons between these symmetrics cannot have this additional symmetry. And that's because the difference in these phonons, or the sum in terms of the theta angles, is actually an overall superfluid mode. Okay, it's the overall.
It's just the
phase.
U1 mode.
It's the U1 mode that says that you have superfluid stiffness. If it's a superfluid, it has to have this stiffness.
Yeah.
Why is the difference about the sum?
Because U minus is actually minus of U plus, it turns out. but okay. It's for physical reasons defined that way. So basically what this term says is that it prefers that this is the current, overall current, and it prefers that current to be 0. Okay. So actually, therefore, what you get is, you get this system, as I'll show, is really a sum of an XY model for the overall phase, for the superconducting phase, and it's a symmetric just for the phonon mode. Okay.
Yeah, can I ask you a question?
Yes.
So, are there some observable implication of this symmetry, of the fact that this term
Yeah.
is 0?
Yeah, that's what my talk is about. Okay, the story is, okay, I'm going to skip over this. Okay, so what you get is actually infinitely anisotropic superfluid. Let me maybe skip over this.
Don't worry about time.
Okay. Okay. So the fact that you get a stiffness, superfluid stiffness, in the direction parallel along Z, is just a statement that the system would like to have a balanced current between Q and minus Q component. So that's why you immediately get a stiffness. Here it is. Well, let me put it here. For the derivative along the wave vector. But in the model without this additional coupling, so this additional stiffness also enforces that there's a constraint or energy penalty for these two components not to align with each other. Okay, so there's a stiffness for misaligning the wave vectors, Q and minus Q, and there's this in terms of the magnitude, and there's a stiffness associated with misaligning the direction. The misaligned direction is much softer than misaligning the magnitude. So, and that's what this term represents. It contains in it this additional contribution, energetic contribution of misaligning the direction between the Q and minus Q component, which is just a transfer superfluid stiffness, as you will see. And so as a result, what you get is you get a symmetric elasticity for the phonon mode, and you get highly anisotropic elasticity for the superfluid mode. There's a rho s perp and rho s parallel, and it's not just, I mean, it's this anisotropy between rho s perp and rho s parallel is in a sense qualitative, in the sense that the ratio is actually vanishes as you approach HC2. And the reason is because this superfluid stiffness, the rho s perp, comes from a quartic term, so it's proportional to delta Q to the fourth. While this superfluid, while the rho s parallel, this mechanism comes from just a quadratic gradient of delta squared. And so they're actually different by powers of delta. And so when you approach HC2, this ratio actually vanishes. So you get a state which doesn't have any superfluid systems in the perpendicular direction. So anyway, so now that you have this theory, you can now explore everything. You can now explore it. You can ask, okay, what do in a serious way, not some Hartree-Fock, not some just microscopic way, the way you explore gently fluctuations. You really can explore it in a serious way, okay? Because now you really have the right variables. So you can explore quantum fluctuations. And the first thing you find, I mean, so original motivation was I thought this, because I anticipated this very soft, like Goldstone elasticity coming from the symmetric physics that I described over here. And so I thought maybe this will give you something that even at 0 temperature is going to be disordered, which would be really exciting. So a ground state which in mean field is ordered, but beyond mean field theory, when you include quantum fluctuations, is disordered. It turns out that does not happen. Okay? So if you go and take this theory and calculate the magnitude of the order parameter, it's non-zero. So these fluctuations, both in the phonon and in superfluid phase, are finite, as long as you're in dimensions bigger than 1.
And then it takes us, me and Jora, back to our question. So if d equals 1, the state is unstable, right?
It's unstable in the same way as the XY model, 2D XY model, 1 plus 1 dimensional XY model is unstable. But it still doesn't mean the state is not distinct from some other state. Okay, so that's what we'll describe, right? So you could have vortices that unbind.
In 1D there are no vortices.
Not in 1D, but so what I'm saying is that's not, in 1D it's just there's nothing else. Once that spin gap closes, there's nothing else.
That's like
and then you just have a Langer liquid. Okay, so Larkin-Ovchinko state is stable to quantum fluctuations. That's the message. Okay, So what happens at finite temperature? Well, so at finite temperature very much depends on whether you look at 2D or 3D, but so the superfluid, so if you're above 2 dimensions, since this just obeys standard XY physics, above 2 dimensions, as long as you're not in 2 dimensions, superfluid phase is stable. Superfluid order is stable, so theta doesn't grow. So it's stable to thermal fluctuations. But the phonon mode, because it's, now let me put this up here. So the phonons, H phonons, go as K over 2 graph perp squared U squared plus B over 2 dZu. So this is going to be the main actor in what I'm discussing and leads to all the interesting physics. This, if you have a ghost thermal with that kind of a dispersion, it behaves in 3 dimensions the way XY model behaves in 2 dimensions. Namely, in 3 dimensions, it's quasi-long-range order. So the positional order is unstable in 3 dimensions or lower. Now the order parameter, recall, well, okay, so there are many consequences of this. So first, Larkin-Chichikov superfluid, which I'll designate as superfluid symmetric, it has quasi-Bragg peaks in 3D. In 2D, there will be Lorentzian. They'll occur at some multiples of twice the wave vector that we discussed. And it has all kinds of interesting physics that follows that I'm not going to discuss here, one, because I'm running out of time, and two, because it's the standard physics that we know and love in liquid crystals, okay, that people have explored it. And in fact, here it's happening in this superfluid background. There's a fixed point that controls it, etc. There's all kinds of interesting. So the other observation is, well, another way to summarize that observation is, it sounds like an oxymoron, but it's actually true because of this. This is the Goldstone mode theory for the phonon. Even if you're in 3 dimensions, even though the phase is ordered, this part of the of the order parameter is ordered, this part is disordered. And since the order parameter is not a sum of the 2 order parameters, it's really a product. When you disorder the phonon, even if there are no dislocations, it's just you disorder just the elastic phase fluctuations or phonon fluctuations, it destroys this Larkin-Ovchinnikov order parameter. So in other words, in 3 dimensions, the Larkin-Ovchinnikov phase has 0 Larkin-Ovchinnikov order parameter.
But there is a Powell order, though.
Absolutely. So it's distinct from something else that I'm going to talk about in the same way that in 2 dimensions we know very well, you know, we have a parallel phase, it's distinguished topologically. So you could say this phase, Larkin-Ovchinnikov phase is a topological phase. It's distinguished not by some lambda order parameter from some disordered version of it, but it's distinguished by, you know, topology. It's distinguished by whether vortices or dislocations proliferate or not.
Am I right that that's a topological number which is preserved to just the number of layers?
That's right, exactly. That's what a dislocation is. A dislocation, if the dislocations are not present, then you can tell, no matter how far you go, those layers could be going crazy, but nevertheless they're elastic. You can
how many of them do you have in your system? Because it's well defined.
Absolutely.
There is no admixture of states with different number of domains.
Right, exactly. So, and then just for the
record,
record,
it's a gauge theory, basically.
Just for the record, this is the U1 cross U1 theory, but it's mod Z2. And mod Z2 has to do with it's a product of 2 order parameters. That's going to be important. It determines what kind of topological defects I can put in. And so at this point, it's very simple. Okay. So what can I do? And it's nice whenever you have phases. Whenever you have these topological-like phases that are not characterized by an order parameter, it's much more productive to go to the ordered state and describe what can happen in terms of proliferation of defects, because then you can capture phases that you could not capture by a Landau order parameter, since you already know you will have phases like this. It's very much like 2D XY model. We couldn't, if we were working with an order parameter, we could never describe the existence and its distinction from the disordered state. So what kind of defects can you have? Well, you can have you can have a dislocation, and this is how it's described. It's basically you insert a plus-minus domain inside a minus region. And so I'll indicate that by 2 integers. So defects are going to be indicated by 2 integers. First integer tells you what the defect is in theta, and second integer tells you what the defect is in the phonon. Okay? So 0, 1 is a simple dislocation. It looks like this. Okay? So it destroys Larkin-Ovchinnikov order, and it completely destroys periodicity. But it doesn't destroy completely superconducting order. Because what it does is, if I square this order parameter without complex conjugating it, so there's still an order parameter. There are two secondary order parameters. This one, which will go as e to the I 2 theta, and there's another order parameter which is magnitude squaring, which goes as cosine 2q z plus da da da. So even when I destroy delta, by, let's say, unbinding dislocations, I can still have this order parameter around. So that would be, this is a route, unbinding this guy is a route to creating charge 4e superfluid. Okay? It's a superfluid in which this order parameter has disappeared, but its square is still around. And the square of it is not affected by dislocations because it has a homogeneous component. And so this is also a good point to point out that this is this state, even though it shares with a supersolid the feature that it has both break translational symmetry and has optimal long-range order, it's distinct from it because it doesn't have a q equals 0 component. It only has non-q, finite q component. And so as a result, when you restore translational symmetry, you immediately destroy the order parameter. The order parameter is a product rather than a sum. Okay? So that's one kind of defect. The other kind of defect is, of course, 1-0 defect, and that's a vortex. And so that means your deltas is alternating plus minus, but on top of that background, you have also vorticity in that sign. Okay? So you don't have just a real order parameter, it's not just real. So again, when you unbind these guys, you can still have, you destroy the superfluid state completely, but you can still have periodicity at twice the wave vector. Okay, that's what I say here. But now in addition, you have fractional topological defects, and these are really, well, okay, so these are the novel ones. Namely, if you insert half a layer, half a domain wall between plus and minus, so these I would designate as pi vortex. When you insert half of this layer, your wave function, the cosine, will change sign. Okay? But that can be compensated by putting a half a vortex that will exactly kill that change of sign, and therefore make this single value. So that means I have half of a dislocation, but I have to have half a vortex attached to it. So that's and there's really two types of defects on this. There's a half-half and half-minus-half. Those are distinct. And that's the reflection of the C2. This is in terms of sort of complex order parameters, this is what it looks like. So that kind of a defect destroys completely both the superfluid order and then translational order. Okay, so now that we understand these defects, so now it's very simple. So now you ask, what can happen to the Larkin-Chinka state if I now proliferate some of these defects? Well, the simplest thing is, there are many things that can happen, but the simplest thing that can happen is you have this Larkin-Chinka state described by your Larkin-Chinka order parameter, which is actually not even there even without the defect, for the reason I described, because the phonons, even in 3 dimensions, thermally destroy this order parameter. And then what you do is you unbind you unbind dislocations, and what you will get is a state that doesn't have translational symmetry, or the translational symmetry is restored, is going to be a charge 2 4e superconductor. It's going to have twice the phase rotation. But in principle, if you just unbind dislocation, you will have orientational order. So it's a state in which the number of layers is not conserved. But there's still a direction, orientation of Q is conserved. So that's what you would get as a charge 4e pneumatic. There's no way to get away from that. I mean, of course, if you could always have a first order transition and destroy the phase and go all the way to the normal state. But if you want to do it in a continuous way, there's no way to avoid this kind of a state. And then, this state can further, there are various scenarios, but this state can further, if you now disorder the orientations, which is ordered here, you'll get something like a pneumatic and a uniform superfluid. Isotropic superfluid. So this is in the same universality class as just the BCS singlet superfluid. In a sense, what I'm doing is I'm going down like this. Okay, so let me put this all together. So what kind of a phase so inside this little region that I spent a long time arguing that it even exists, motivating that it might exist, let me actually ask what's inside here. And what I'm going to try to argue is that, as a summary, is that that guy consists of many phases. Okay, and I don't know if I'll be able to get through all of them. So here's the picture, the full picture. So here's my BCS superfluid over here, and it's so I'll call it superfluid isotropic. Here's my Larkin-Ovchinnikov smectic, and here's my isotropic normal state. Okay, but now imagine I go down, and when I go in this direction, I make translational order more and more flimsy, because my domain walls coarsen and become further and further apart. So whatever interaction they have becomes weaker and weaker. So eventually, the dislocation, to put a dislocation into that order, will be cheaper and cheaper. Okay? So when I go down here, eventually, those dislocation objects that I discussed in the previous transparency will unbind. When they unbind, I'll go into this, namely 0A will unbind. I'll go to a superfluid pneumatic, which has charge 4E. 4E, this is not charged, but 4 atoms. So it's a state which has 4 atoms paired together. Over 4 atom cluster condensate. Okay? So on the other hand, if I go in this direction, I'm going towards the normal state. So I'm disordering the superfluidity. I'm trying to destroy the superfluidity. So at this point, as I increase in this direction, let's say I'm sitting at 0 temperature, I'm now going to unbind 2 pi vortices and no dislocation. Okay? If I do that, I'll go to a normal state, but with a periodicity that's twice the wave vector of the original periodicity of this original state. So okay, so these are conventional transitions. Now, if I go further, once I've unbound these vortices, I can unbind, in their background, I can go and unbind the dislocations. If I do that, these integer dislocations, I go from a Fermi liquid that had periodic order to a Fermi liquid that's pneumatic now. It's namely has orientation, but it doesn't have, number of layers is not conserved. It has dislocations. Okay, so very quickly it's going to look quite unbelievable. Okay. But I appreciate you bearing with me. Okay, so on the other hand, there's another way I can leave this phase, or this phase. I can just, rather than unbinding 2 pi zeros, vortices, I can unbind half-half vortices. Half-half topological defects. Half dislocation bound to half vortex. So, and then I get a Fermi liquid, pneumatic Fermi liquid. Now, it's very easy to show that this state, well, you can see it here, is not only distinct from this state, it's distinguished from this state by an order parameter, namely just lambda order parameter that tells you that there's a periodic order here and there's no periodic order here. But it's distinguished from this Fermi liquid pneumatic state by topology. Namely, in here, you don't have fractional defects, and here you do. So that's why, so this state in the old language one would call, or sort of a language from studies of spin liquids and correlated electronic system, you would call this you would call it a start phase. Namely, this is a fractionalized phase. It's a state, one way to get fractionalized phases is by unbinding non-fundamental defects. Pairs or some kind of a higher defects that are not fundamental. So if in a sense, unbinding this defect or this defect, this is a composite defect. It's made up of one of these and one pi a over 2 and pi minus a over 2. So in other words, this phase, although from the Landau's point of view it's disordered, it has still some rigidity left over because it has pairs of these guys unbound, but not individual guys. And so as a result, it can be distinguished in this topological way. So similarly here, you can, once you go to here, you have a superfluid state that's pneumatic order, but it's distinguished from another superfluid, Fermi liquid state, which has these fractional defects unbound.
Leo, so in 2 dimensions, can you have that boundary where you proliferate fractional defects? Because don't they cause logarithmic divergence?
So that's, okay, so this is, I should have maybe said this. It turns out, this phase center will be different in 2 dimensions. So one important observation is, in 2 dimensions, dislocation costs finite energy. And that's because this energetics is much softer than the XY model. So in 2 dimensions, rather than being logarithmic, it's just finite. It costs basically energy k. And so that's an amazing thing. It means at finite geometry, 2 dimensions, the defects you're going to unbind, you're going to immediately unbind this guy. And that's a composite defect from the point of view of these halves. So you immediately, in 2 dimensions, put yourself on this phase. So many of these bonds will be erased. But what it importantly proves is that this fractionalized phase appears before you get into this more conventional phase. Back in the late 90s, people were trying to, there's this famous Sentinel experiment that was proposed, where they're trying to understand pseudogap state of a high DC superconductor as some kind of a fractionalized state in which pairs of vortices have unbound, but individual, in other words, HC over E vortices have unbound, but not HC over 2E. So that would be a state that's a normal state in the sense of it doesn't have superfluid order, but it does not completely disorder because only pairs are unbound, but not individual vortices. But there it was very hard because you were playing with, for ordinary vortices, a pair of vortices are costlier because they have coefficient of 4 in front of the log compared to the fundamental vortex. For me, this analog of the pair of vortices, this composite defect, is cheaper than this individual defect. So I have no problem going to this fractionalized, so-called fractionalized phase.
Remind us, what was the outcome of that central experiment?
It was looked for experimentally by Kim Moeller, and nothing was found.
Thanks.
Yeah, no, that's fine. I'm trying to connect to something that...
No, I just...
It's fine, yeah.
I discover people's memories fade away, so I just wanted you to...
Yeah, no, my memory is not...
I couldn't quite remember.
I'm sure, somehow I think you could. Anyway, so now you can talk about what happens in finite geometry. I'll spare the details, but basically, now I have this Goldstone model. I really want to put it in the trap and ask what happens in the trap. All kinds of interesting stuff happens. So you have this Larkin-Chichikov-like state. We know, and I talked to you about it in the experiments, in the trap, what the system wants to do is it wants to expel. The chemical potential is varying in this LDA approximation. So what it wants to do is put magnetization outside, expel the magnetization. And so the way it does this in the Larkin-Chichikov way is it creates a divergence of this distortion. So the polarization or imbalance is really just a divergence of U in the Z direction. So what it does is it creates a compression of the Larkin-Chichikov state at the boundaries. So and you'll get the polarization concentrated outside of the sample, and this is how it does it. So it's a non-trivial sort of elasticity problem that one can solve. There's also other candidate states. So once the trap is sufficiently tight, one might question whether this kind of a small deformation, elastic deformation, cannot be beat by something that's like an onion-like concentric state, where you now have Larkin-Chichikov state running in this direction with a variable Q. So the Q is varying smoothly. Okay, you can talk about fermions. So everything I've talked about is Goldstone modes. But in principle, there are fermions. There's actually those fermions that couple to these Goldstone modes. So how can they couple? Well, superfluid current can couple to fermionic current. You can understand what that does. And it doesn't do much. It gives you Landau-like damping of the Goldstone modes, but in a very gentle way, unlike gauge field coupling to the current. So we can talk about that in more detail. There's also density coupling to the grad theta squared, to the current, to kinetic energy. That's also very benign, because the lowest order, this is just the density of the fermions times the grad theta squared. So that doesn't do much. It just renormalizes the stiffness. There's also other kind of atom-phonon coupling, much like in the Froelich Hamiltonian. You've got those kind of coupling. They're also pretty benign. So again, so I said what they do. There's a weak Landau damping and finite corrections to the parameters that I've described. Okay, so let me talk about experiments. Just finish with talking about experiments. So once I'm in a trap, all this infradivergent physics, this order parameter vanishing with divergent long-scale fluctuations goes away, because now all my lowest Q mode is cut off by the inverse system size. So as a result, my Larkin-Chichikov order parameter no longer goes to 0. It goes to 0. It's finite, but it goes to 0 with some eta exponent in 3 dimensions as a function of system size or number of particles in the system, or as a function of trap frequency. It goes to 0, but it's finite, so I can really explore that. Vortices in this system are anisotropic because of this very large perpendicular longitudinal superfluid density, superfluid stiffness. So vortices will look like this, and these would be the symmetric layers. Then you can imagine making, so one way to probe, I predicted that in the system you can have these fractional vortices with fractional vorticity, half vorticity. So that tells you that the relation is now this additional factor of 2, relation between the rotation of this object and the vortex lattice density, or the vortex lattice constant. You can look at the momentum distribution function or structure function. Equally, I already mentioned you'll have this universal power law-like behavior. So in the time of flight, you will see peaks at a finite position. You won't see a central peak, but you'll see a peak that's removed, and that's a measure of the Q naught. Okay, and I'll just leave you with the summary. So thanks very much.
So basically, can I be back to my question about the effects which follow from the fact that this term is 0 by a rotational symmetry, because you were saying that all the rest of the talk will be about that, but somehow I was not able to see why that was crucial. So
okay, let me
can I reformulate my question? What will happen if this term is different from 0?
Okay. If this term is different from 0, which is what, for example, if you're exploring Larkin-Ovchinnikovs in crystalline environment or stripes in superconductor like Kibelson and Frakin are doing, then you can try to call it a liquid crystal like they do, but it's a useless term. What will happen is the phonons, then you go thermal theory. So this is some crystal, inside crystal. Your Goldstone-Moore theories is basically grad theta squared plus grad u squared. And that's it. That's the end of it. So that means in 2 dimensions, of course, you have power law phases and something interesting. But in 3 dimensions, they'll be long-range ordered both positionally and...
It's good enough.
It's good, and that's it. And so that means qualitatively, your mean field description that you got from BCS or wherever is qualitatively correct, in the sense that there's an order parameter, it's non-zero, it's but it completely goes wrong in trap, because their Goldstone-Moore theory is grad theta squared plus, grad perp squared u squared plus dz u squared. And so as a result, and since the order parameter is a product of eta I phi, if you wish, and eta I u plus qz. Okay? Okay? As a result, this divergence that you get even in 3 dimensions, in 3D divergent, destroys this order parameter. So in no sense is the mean field description even qualitatively captures what the state does, even in 3 dimensions at finite temperature. So that's really the, I could have just done this and spared you an hour and a half. Yeah.
So my question is actually turned out to be connected to the first question, even though I didn't want it. So if one really insisted, one could write this as a gauge theory. And in the first example that you explained to us, the gauge field itself would be massive. Whereas in the second example, it would have been massless. And these 2 theories then differ like heaven and hell.
Exactly. So in fact, there is a gauge description. You have this product guy. So what you can do is you can treat this as an independent particle, much like, let's say Central talking about spin liquids. You can call this a boson. You can call this some other boson, B1 and B2. They're tied together, but you can decouple them and write a theory for this, write a theory for this, but then there's a gauge field that they both couple to that glues them together. And the point is that, so the gauge field is important here.
So connecting to that, when you showed your phase diagram, in principle you could write it also as kind of Desgen-inspired gauge theory when you look at your symmetric to pneumatic transitions. If you do, in principle, then again, you could use mean field theory of the fluctuation action to compute the phase boundaries of your phase diagram. Have you thought of doing that? And would anything interesting happen? Because they often tend to be first order transitions.
Yeah, so I have not done it. And so there's a lot of things I'm trying to do in this follow-up, long, detailed article. But it's sort of like part of the motivation is missing, because until there's some indication that this phase exists in experiments outside of one dimension, it's tough to motivate yourself to do kind of these now, effective of an effective theory, and building an effective theory and exploring all this rich physics on top of something that you build that is kind of, has not even been realized in the most basic way, right? So first they have to find some experimental manifestation of a finite wave vector. Once they do, then
maybe there's a graduate student whose character needs to be built up or something.
Say again?
Maybe there's a graduate student whose character needs to be built up.
No, of course. I mean, you saw there's this very rich phase diagram, and I don't like to do this. I usually like to write one paper and just be done with it. But you can each one of these could be a separate, study, right? The phase transitions here and all the detailed properties of these phases. They're distinct phases.
How do you get the phase diagram? You just read it off, from the.
So this phase diagram, I have to just to make sure, full disclosure. This is a cartoon rendition. I don't know these phase. This is a one consistent way to put together all the ingredients that I told you about. Namely, I have 3 types of defects, 2 types of integer defects, and 1 type of fractional defect, or really 2 types of fractional defects, plus and minus. And all I do is the most gentle, unbiased unbinding of those defects, guided by some energetics of this theory that I understand very well. Okay? But now, if I want to do detailed theory, there's a, you can just, let's say in 2 dimensions, you would do some, Kostelos-Talos like unbinding of these defects. In fact, like I said, in 2 dimensions, these defects would unbind immediately because they have finite energy. So I have a dual theory that describes all this. So in principle, all those boundaries can be described in detail. Certainly, if you tell me what these parameters are, what these coefficients are, then I can calculate them with certainty. Okay, I can calculate those boundaries with certainty. It's just that what microscopics, now this is already once removed from the microscopics. And so then I have, I don't have them in terms, and that step is the stuff that I have it, but only in the BCS limit. But, if you go to AMO experimentalists, they're going to say, they'll listen to you very carefully and they'll say, well, this is very impressive, but is it true for lithium as well as rubidium or something like this? So there's somewhat mismatch of appreciating this kind of physics versus microscopic physics.
But so is it fair to say that, just kind of to summarize, maybe you said it already, that so if you're in large Markovnic states and you're trying to go by changing parameters into either BCS or the normal states, there's no way to get there by a second order phase transition without crossing one of these intermediate phases.
That's right. In mean field theory there is, but once there's no way. It's non-generic. You can fine-tune it to be that, but it's non-generic. In the same way that an isotropic...
in principle, you could fine-tune, so that's...
I can fine-tune parameters that I never go through this phase. That's
and go directly into
that's
this.
right. But it's I just have to fine-tune certain fugacities to be infinite or very large. Okay, but it's just not a natural way.
So in 2 dimensions, how many different phases do you find out of these kind of conditions?
Okay, I don't want to hold people up, but we can discuss it in private.
Yeah.
But there various boundaries will disappear in 2 dimensions because certain defects, dislocations are finite energy. And so if you erase those boundaries and those distinctions, then you'll get it from this phase diagram. But we understand it.
For questions, let's thank the speaker. So there is a new